especially as far as like my general outline of like the order I'm going to present things in, I'm going to be following Schwartz. But just FYI, like a lot of the actual derivations are either like things coming from Peskin and Schroeder, things from Srednicki, things from Schwartz, things from Coleman's field theory lectures, field theory class, and also just random things that are not from a textbook. But as far as global outline, I will keep following Schwartz. Okay. Good. One other announcement, there were a couple typos on the problem set, all metric signature related, I believe. So as most of you noticed, I got a couple emails. In the gamma matrices, the way that I wrote them, I claimed they were all Hermitian. 3 of them are anti-Hermitian instead of Hermitian. There's some I's instead of minus signs. Is that all clear? Should I send an email clarifying this? Maybe I'll send an email clarifying this. So again, if you haven't yet sent me your email address and you're not registered, send me your email address. Also, I think when I wrote out the electromagnetism problem, maybe it was problem 4, I very explicitly used the wrong signature at some point, so I apologize for that one as well. So I'll send out an email, hopefully later today, explaining, hopefully, what I was trying to say. So sorry about that. I can promise you that it won't be the last time I make a mistake because I used the wrong signature. It might not even be the last time today. Okay, we'll see. Okay, today what I wanted to do was finish our discussion of classical field theory and then describe, at least very briefly, the Hamiltonian approach to classical field theory, which is useful because Hamiltonian approaches to mechanics very naturally lead into quantum mechanics. So we'll finish our discussion of classical field theory, and then we'll move on to discuss the quantization of classical field theory. I'll first quantize free quantum field theory, and we'll see that this immediately will reproduce the whole business that I introduced last week with the Fock space and with the Hamiltonian and the infinite number of decoupled harmonic oscillators. And this will lead us into next class, our discussion of interacting field theory. We'll talk about the LSZ formula and the basic and scattering processes and how we're going to go ahead and start computing these things in interacting quantum field theory. Okay, so let me just begin by reminding you of a few things that we discussed last class. So in a classical field theory, the degrees of freedom are some field that depends on position as well as on time. And this should be contrasted with, for example, more traditional classical mechanics of a finite number of degrees of freedom, where you have some degrees of freedom that are labeled by some index I, and each one of these degrees of freedom depends on time but not on position. And here you should think of classical field theory as the generalization of classical mechanics, where this I label that labels the different degrees of freedom in some classical mechanics system is replaced with a label X that tells us that we have 1 degree of freedom per point in space. And many of the complications of classical field theory are just natural generalizations of classical mechanics where we do things like replace the sum over I by an integral d3x. Okay. For example, the dynamics is determined by the minimization of an action, which is the integral of some local quantity called the Lagrangian density that is a function of the field and its derivatives. And this is, of course, the generalization of the action of classical mechanics, which is an integral dt of a Lagrangian. And then the Euler-Lagrange equations are determined by demanding that the infinitesimal variation of the action, as one varies the field configuration, that is to say, as one varies phi of x, is equal to 0. So this is the variation of the field with respect to phi. So that's the derivative of the Lagrangian with respect to phi minus the derivative of the Lagrangian, the derivative of the derivative of the Lagrangian with respect to the derivative of phi. And of course, if we have many fields, we could label them by some index. Let's call it I here. And then there would be one equation of motion, that is to say one Euler-Lagrange equation, for each one of those fields. So for example, if you're considering electromagnetism, you would have 4 fields. The 4 components of the electromagnetic potential, A mu, and you would then have 4 equations of motion coming from varying the action with respect to each one of those 4 independent fields. We began last class to discuss special properties of these equations of motion in cases where our theories have symmetries. So in particular, if we have a continuous symmetry, that is to say, a one-parameter family of symmetries, which are changes of our field variable phi, then under an infinitesimal continuous symmetry, where phi goes to phi plus delta phi, the action is invariant. So the variation of the action is equal to 0. And in particular, if you think about it, what does this mean for the Lagrangian? This means that the Lagrangian density, as one performs this continuous symmetry transformation, must be a total derivative. So it has to take the form of d mu q mu for some vector q mu, so that the variation of the action is equal to 0 under this continuous symmetry. But then you could go ahead and compute directly the variation of the Lagrangian under the transformation where phi goes to phi plus delta phi. And what do you get? Well, you get one term, which is just the equation of motion times delta phi. And then you get a second term, which is the boundary term that we discarded, the total derivative term that we discarded in our derivation of the Euler-Lagrange equations. And then comparing these two expressions for delta L, we see that the quantity J mu, which is the variation of the Lagrangian with respect to the derivative of phi times delta phi, minus q mu, will be a conserved current. So that d mu of J mu, the the Minkowski space version of the divergence of the vector field J, will be equal to 0. Okay. So is that clear? That's the derivation that we went through last time. And last time I gave you a very simple example of a computation of a conserved current. And I'd like to begin today by giving you another slightly more interesting and more sophisticated example of a conserved current. And it'll be a conserved current, in fact, a set of 4 conserved currents that will be conserved in any field theory that we're going to be considering in this class. Before I do that, let me just pause and see if there are any questions. So if anything's not clear, then hopefully it'll become a little bit more clear when I work out this following example. Okay. So let's consider the following symmetry. So we're considering theories that are Lorentz invariant and are invariant under translations. So let's ask what that tells us about the conserved quantities of the theory. So let's imagine doing a translation where the coordinates shift by an amount given by some vector zeta. Okay. Zeta is just some 4 vector. Could be anything. For example, if I want to consider a time translation, then zeta would be a 4 vector with components only in the time direction. Okay. So the action is supposed to be invariant because the theory is translationally invariant. So delta S is equal to 0. Now how do the fields phi transform under this translation? Well, phi goes to phi plus delta phi, where at leading order, when zeta, this vector zeta, is very small, delta phi is just given by the Taylor expansion. So it's zeta mu d mu of phi. That's just the first term in the Taylor expansion, where phi at x mu plus zeta mu is equal to phi at x mu plus the first derivative of phi at x mu plus higher order terms. That's just the four-dimensional Taylor expansion. And the Lagrangian of the theory is not going to be invariant. But because the Lagrangian density is a scalar, it will also transform in exactly the same way. Sorry, I can't draw an L here. In particular, delta L is equal to zeta mu d mu of L. So plugging this in to our formula, we see that we have the following conserved quantity, the following vector, j nu, which is the derivative of the Lagrangian with respect to d nu phi, times the variation of phi, which is zeta of mu, d mu phi, minus q mu, which in this case is zeta of mu, times L, is going to be conserved. Sorry. That's a zeta of nu, of course. Because, yeah. Here, it's important to remember that, I can always relabel my indices. So because delta phi, I had a mu index here, I chose nu as the free index in this equation here rather than mu. And so I'm just going ahead and plugging into this equation here with mu replaced by nu. So for each choice of 4 vector, zeta mu, this is a conserved quantity. So what we have here, so there's a 4-dimensional space of vectors zeta. So what we actually have is a 4-parameter family of conserved currents. Okay? And it's conventional, so we have a 4-parameter family of conserved currents, each of which has 4 components. So it's conventional to package this into a 4x4 matrix, or a tensor, which is called the stress tensor of the theory. Okay? So in particular, what I'll do is define the stress tensor. So I'll just write this as T nu mu zeta mu, where the stress tensor T nu mu is the derivative of L with respect to d nu phi times d mu phi minus g mu nu times L. And this 4x4 matrix, or 2, 0 tensor, is known as the stress tensor. Now, in your earlier classical mechanics classes, you hopefully learned that there are conserved quantities associated with translations. The conserved quantity associated with time translation being energy, the conserved quantity associated with spatial translation being momentum. This stress tensor that we've written down here is the analog of energy and momentum in a field theory. That is to say, a theory with local degrees of freedom. So in particular, it is the set of 4 conserved currents associated with translations. If you want to construct quantities from this that are conserved, that is to say, are independent of time, then we just do what we did last time, which is remember that if we have a conserved current, a quantity j mu such that del mu j mu is equal to 0, then the integral d3x of j0 is time independent. And that's just proven by taking the first derivative of q with respect to time, replacing j0 dot by del dot j vector, and then that's the spatial integral of a total derivative, so it's equal to 0. Okay. So it's instructive to work this out in the present case. So for example, the energy of the theory is the integral d3x of the conserved current associated with time translation. So that's t0, 0. So that's the total energy, telling us that we can identify t0, 0 with the energy density of the theory. So this is really the difference between Noether's theorem for a field theory versus a classical mechanics system. For a classical mechanics system where you just have like 1 or 2 degrees of freedom, the conserved quantity associated with time translation is energy. Here we have a local field theory with 1 degree of freedom per point in space, and so we get not just a total energy, we get an energy density. And likewise, if I integrated d3x t0I, that would give me the momentum as an integral of a momentum density. Any questions on this before I continue? We'll be returning to stress tensors again, don't worry. Okay. So let's just write out exactly what t0, 0 looks like in the present case. So I'll just lower those indices to make life convenient. So what is that? That's dl by d phi dot times phi dot minus L. So hopefully this should look at least a little familiar if you remember the Hamiltonian formulation of classical mechanics. Okay. So in particular, so let me just remind you of the Hamiltonian formulation of classical mechanics. So traditionally, there are 2 ways of formulating the laws of classical mechanics. So in the Lagrangian formulation, you characterize a system by a set of dynamical variables qi and a Lagrangian that depends on qi and qi dot. And then you write down the Euler-Lagrange equations following from these. In the Hamiltonian formulation of classical mechanics, one characterizes the theory in terms of a set of dynamical variables qi along with some conjugate momenta that I'll call pj. And the dynamics is determined by a Hamiltonian that's regarded as a function of the q's and the p's. And instead of the Euler-Lagrange equations, the equations are determined by the Hamiltonian equations of motion, namely that qi dot is equal to the derivative of the Hamiltonian with respect to pi, and pi dot is the derivative of the Hamiltonian with respect to qi. Or, more generally, an observable of the theory is some function of the q's and p's, which obeys an equation of motion that says that ai dot is the Poisson bracket of A with the Hamiltonian, where the Poisson bracket of 2 functions is just given by, say, the Poisson bracket of f with g, where f and g are functions of p and q, is the derivative of f with respect to qi times the derivative of g with respect to pi minus the thing with the q's and the p's reversed. Okay. So this is the Hamiltonian formulation of classical mechanics. The primary advantage for our purposes of the Hamiltonian formulation of mechanics is that it's very easy to quantize a system once you've written it in its Hamiltonian formulation. In particular, quantization, at least naively, is the procedure whereby each observable A is promoted to some operator, sometimes denoted A hat. And the Poisson brackets are promoted to commutators. So the commutator of two observables is equal to IH bar times the Poisson bracket. So I guess usually we write that as the Poisson bracket then becomes 1 over IH bar times the commutator. So for example, the Poisson bracket of a P with a Q is equal to 1, which gives us the fundamental commutation relation of quantum mechanics, that the commutator of P and X is equal to IH bar. And the only thing now that is lacking is the dictionary that relates the Lagrangian and Hamiltonian formulations of mechanics, which is that given a Lagrangian that specifies the dynamics of some particular system, the momenta pi conjugate to some degree of freedom qi is just dl by dq dot, and the Hamiltonian is equal to pi qi dot minus L. Okay. Yes, question. Yes, sorry. I'm trying to usually... Oh, sorry, yes, thank you. Indices misplaced all over the place. Good. Thank you. Good. Okay, so this was a lightning review of the Hamiltonian formulation of classical mechanics. And I would like you to compare this expression here. H is dl by dq dot times q dot minus L with this expression here for the energy density in a classical field theory. So the energy density is dl by d phi dot times phi dot minus L. Okay. You can see it's exactly the same thing. Okay. All we do here, so in particular, the Hamiltonian formulation of classical field theory is exactly the same as the Hamiltonian formulation of standard classical mechanics, except that in field theory, the QIs are replaced by some phi of x. So in particular, for every field phi, there is a conjugate momentum, and just as a field phi depends on space as well as on time, the momentum conjugate to a field phi depends on space as well as on time. So that's defined to be the derivative of a Lagrangian with respect to phi dot. And the Hamiltonian of the theory is the integral d3x of some Hamiltonian density, which is equal to pi phi dot minus L. And as we saw above, that's precisely the energy density, namely the zero component of the conserved 4 vector associated with time translations. Okay. Just as in classical mechanics. Okay. So in principle, we could only, if we wanted to, we could work only with the Hamiltonian formulation of classical field theory instead of the Lagrangian formulation. And I'm introducing it now because what we're going to do next is we're going to quantize the free quantum field theory that we introduced last class. And in particular, when we work out the algebra of operators in this theory, it's very useful to do so by remembering the analogy with classical mechanics. So in particular, to quantize, we must impose the canonical commutation relation, okay? So which says that the commutator of an operator phi of x with the conjugate momentum pi of y should be equal to IH bar times the delta function x minus y. So this is just the analog of the So I'll even put some I indices there. Let's call it. The fundamental commutation relations of quantum mechanics, of standard quantum mechanics. Yes, question.
Why do we want the pi to be at the same time?
Ah, good. Yes. So that's the next point that I was going to note. Okay. So this is an equal time commutator. We could, of course, compute the commutator at other times, and indeed we will, either this class or next class. But the point is that the commutations that we impose in quantum mechanics are commutation relations between operators x and p, and you need to decide how those operators are going to evolve in time before you decide what the commutation relation at some later time is going to be. So in particular, well, in the simple case of standard quantum mechanics, where things evolve with a time-independent Hamiltonian, then you could either work in Schrodinger picture or in Heisenberg picture. And then in either case, there's actually no difference between the in those cases, the commutators are time-independent. But you could also imagine computing, for example, commutators between x at some time t and p at some other time. Okay? And in that case, commutators would not between two operators would not necessarily be time-independent. Okay? So what we want to do right now is just focused on, say, the t equals 0, t is equal to 0, and look at these equal time commutators. Just to make the analogy with traditional quantum mechanics. And then later on, we're actually going to investigate in a great deal of detail, actually, precisely how this commutator behaves when you start varying these things. So for example, if you put this guy at some time t1 and this guy at some other time t2. Good question. Yeah. Okay. Any other questions? Okay. So let's now just give an example. So let's consider the example of free quantum field theory. Okay. So let's just take 1 degree of freedom, which is a scalar field phi. And the Lagrangian, as we introduced earlier, is the one that leads to the equation of motion being the Klein-Gordon equation. So that's the Lagrangian. So in particular, a free theory is, by definition, one where the Lagrangian is quadratic in the fields. Okay. So I don't know if that's something that I made completely explicit earlier, but this is just our definition of what I mean by a free theory. Okay. And later on, either this class or next class, it'll become clear exactly why that's a good definition for what I mean by a free theory. So for this free quantum field theory, what is the momentum conjugate to phi? Well, it's just dl by d phi dot, which, if you stare at this Lagrangian for a second, it has a 1/2 phi dot squared term in it. So this is just equal to phi dot. And the Hamiltonian density is pi phi dot minus L. So you get, first you have a phi dot squared term coming from here, and a minus phi dot squared term coming from here. So you get a 1/2 phi dot squared term, or 1/2 pi squared. Remember, in the Hamiltonian formulation, you're supposed to phrase things in terms of phi and pi, rather than phi and phi dot. And then you get a term involving the gradient of phi squared, and then you get the mass squared phi squared term. Both of those terms just come from taking minus L. And the important point is that this is a manifestly positive quantity. It's a sum of squares. So that means that this is a Hamiltonian that looks like the Hamiltonian of a perfectly sensible theory. And if you wanted to, you could even, for example, imagine discretizing space, say, and imagining that instead of phi being a function of continuous points x, it's a function on some lattice of points. And then it would be a fairly straightforward exercise, and essentially an exercise that you're doing in the problem set due Friday, to see that this then is a traditional, familiar-looking sort of classical mechanics problem. The only difference being that this kinetic term here, grad phi squared, looks like a potential term when you phrase it in that language. Okay? It's like phi at x1 minus phi at x2 quantity squared divided by the difference between x1 and x2. Is that more or less clear? Okay. So now let's go ahead and quantize this theory using the standard rules of quantum mechanics. And so in particular, last week when we discussed the quantization of free quantum field theory, we sort of started by demanding that the Hilbert space had a bunch of multi-particle states, and then we built the natural operators. Here I'm doing the backwards approach, where I start with a classical mechanical system, this free quantum field theory with its Lagrangian, and now I'm going to go ahead and quantizing it using the standard rules of quantum mechanics. So the first thing that I want to do is, instead of working in terms of phi being dependent on x and t, I want to work in terms of the Fourier transform variables. Why do I want to do that? Well, it's because the solutions to the equations of motion have a very simple form in Fourier space. In particular, they're just plane waves. So they're plane waves of the form e to the I k dot x plus or minus I omega t, where omega here is our old friend, the energy in special relativity, k squared plus m squared. So we can always just expand any field phi in terms of this basis of plane wave solutions to the equations of motion, and it'll take the form integral d3k times some Fourier mode, I guess last time I called it a sub k, times e to the I k dot x, it's called minus I omega t. So that's the mode that goes like e to the minus I omega t. And then there are also going to be solutions that go like e to the plus I omega t. So that's just a general statement that I can always take my function phi and Fourier expand it. Any phi that's a solution to the equations of motion, I can write in terms of this plane wave basis. Okay. And I've left myself a little room here because I'm always free to introduce some normalization there that depends on k. That's just how I choose to normalize my coefficients in this Fourier expansion. And so, for future convenience, I'm going to use the Lorentz invariant measure, integral d3k, over the square root of 2 omega k. So on your next problem set, you'll prove that that measure is Lorentz invariant. Although, for example, if you look in some textbooks, they make some different convention for what that measure factor is. It just will end up turning out to factor into some normalization constants in those coefficients a and b. Now, the next thing that we want to do is impose that phi is real. So it's equal to its complex conjugate. And indeed, you see that when you complex conjugate this guy, you just get this guy, except that k here flips sign when you do this complex conjugation. So that means that B star of minus k is equal to A sub k. So that means that I can rewrite this as the integral d3k over omega k of ak e to the I k dot x minus I omega t, which I'll just abbreviate as k mu x mu using Einstein summation notation, plus A star of k e to the minus I k mu x mu. Okay. In going from this expression here to that expression here, I've done a change of variables where k goes to minus k. Because you would think that this would be A star of minus k, so I just did a change of variables from k to minus k, which introduced this minus sign right there. Here, k mu is the energy momentum 4 vector whose components are omega and k, where omega is the square root of k squared plus m squared. And this obeys, well, essentially the equation of motion that says that k mu, that the 4 vector k squared is equal to m squared. I hope so. Is that the, I always get confused with signatures. Yes, k squared is equal to m squared. Good. Okay. Now, when we go ahead and quantize this theory, so far phi has been a solution to the equations of motion. A is just some set of Fourier coefficients. When we quantize, phi is going to become an operator, and the a's are going to become operators. And what I called A star here is going to become the Hermitian conjugate operator, A dagger. And the algebra that these A's and A daggers obey is going to be the one that follows from the fundamental commutation relation that says that the commutator of phi and pi is equal to a delta function. So let's go ahead and work out what that algebra is. So first of all, what is the conjugate momentum? Well, the conjugate momentum is just the thing that you get when you take the derivative of phi with respect to t. So that's integral d3k over the square root of 2 omega. Well, there's an I that comes down out front. Oh, sorry. There's an I times omega that comes out front when you take the derivative of the e to the I omega t here with respect to time. So that normalization factor is not 1 over the square root of 2 omega, but the square root of omega k over 2. And then you get ak times e to the I k mu x mu minus the complex conjugate. Okay, I'm sorry, actually, is there a minus sign here? Yes, there's a minus sign there and a plus sign there. Sorry about that. So an e to the plus I k mu x mu. Okay. I'm going to try and be careful with these signs. I'm sometimes a little sloppy with my signs. I'll try to be careful. Okay. So the important point is that there's this relative minus sign here that comes because this term and this term, one of them goes like e to the I omega t, the other one goes like e to the minus I omega t. So now what I'd like to do is go ahead and solve for these Fourier conjugate variables A and A star in terms of phi and pi so that I can go ahead and work out the fundamental commutation relations in this basis A and A dagger. So the Fourier transform So let's start by working out the Fourier transform of phi, okay. So what is that? Well, you just get this AK factor divided by the square root of 2 omega. That's coming from this term here. And then in the second term, you get a star of minus k over the square root of 2 omega, because the Fourier transform picks out the term here where this 4 vector, sorry, it's integral dx, of course, because I'm taking the Fourier transform. So that integral dx picks out the term in this expression here. Sorry, there's a lot of arrows there. And that in this expression here, that goes like e to the I kx. So these guys have opposite sign. So it picks out an a star of minus k, and because of, well, that opposite sign right there, okay, you have an e to the minus 2i omega t. And likewise, we can calculate the Fourier transform of pi, and what do we get? Well, there's that factor of I out front, and you get an AK times the square root of omega over 2, and then you get a minus from this minus sign here, omega over 2, a of minus k star times again this e to the minus 2i omega t. So you're going to need to get used to performing all of these Fourier transforms because you're going to be doing it a lot in this course. So I'm going through it in some amount of detail here, but you should hopefully get used to doing it yourselves pretty quickly. Okay. So we can then go ahead and solve for AK in terms of phi and pi. What is it? It's the integral d3x e to the I k mu x mu of, let's see, the square root of omega over 2 times phi plus I divided by the square root of 2 omega times pi. Hopefully, if you remember the harmonic oscillator from classical mechanics, this looks pretty familiar to you. If you remember in classical mechanics, if you have a simple harmonic oscillator, A is equal to the square root of omega over 2 times x plus I over the square root of 2 omega times p. So this is just a statement that in classical mechanics, the raising and lowering operators are complex linear combinations of x and p, the position and momentum operators. And here we see that the same thing is happening in quantum field theory, except now we have a Fourier transform to go along with it. So far, I really have just been talking about classical mechanics, where AK is just some Fourier mode of a solution. But when we quantize, we promote AK and its complex conjugate to operators acting on some Hilbert space, and in particular AK star becomes the Hermitian conjugate of the operator AK. And the basic rule that we impose is the fundamental commutation relation, which is that the commutator at equal times of phi of x with phi of y is equal to 0. That's just the commutator of, like in classical, in standard single particle quantum mechanics, the commutator of x and y is equal to 0. And likewise, the commutator of the momenta are equal to 0. and that the non-trivial commutation relation is the one between the field variable phi and the conjugate momentum pi. Okay. So let's just take these relations here and see what they tell us about the operator, about the Poisson, about the commutators of AK with itself and with AK dagger. Is everything clear so far?
Is there an I that missing out
I'm sure there is. Where's the I missing?
in the second calculator?
Oh, yes, I suppose there is an I missing. Thank you. Good. The Poisson bracket has no I. The commutator is I times the Poisson bracket, or minus I times the Poisson bracket. No, it's I times the Poisson bracket. Thank you. Feel free to let me know if I've missed signs or I's or anything like that. I try to only miss important signs and factors of I. Okay, so let's go ahead and compute the commutator of AK with that of AK prime. So I'm just going to go ahead and plug into this expression here. So what do I get? Well, I'll pull out a factor of 1/2 coming from squaring that factor of root 2. I get an integral d3x when I expand that first AK, and an integral d3y when I expand the AK prime. And I get an e to the I k mu x mu plus k mu prime y mu. And then I get, well, what do I get? I get a commutator of a phi with a, well, I get a commutator, let's just write it out explicitly, of root omega phi of x plus I over root omega pi of y, sorry, pi of x, with the same thing at y, so what is that? Well, the commutator of phi with phi is equal to 0. The commutator of pi with pi is equal to 0. So all you're left with is the commutator of pi with phi. The factors of square root of omega will then cancel. We'll get an overall factor of I that pulls out front. And then we'll get a factor of I times a delta function. So let's see, let's work that out. I times a delta function that sets x equals to y, which we could use to do the y integral. And you get e to the I k mu plus k mu prime sorry, let me be a little more careful here. So let's write this out a little bit more explicitly. Integral d3x, integral d3y. So I'm e to the I kx plus k prime y. Okay, somebody's working hard. Times, well, you have a commutator of this phi with that pi, which is a delta of x minus y. But then you get a commutator of this pi with that phi, which is a commutator of y minus x. Okay. Delta of x minus y plus delta of y minus x is equal to 0. So the AKs commute with one another. Life gets more interesting if you compute the commutator of AK with AK prime dagger. The only difference of this with the computation I just showed you is that there's going to be a minus sign here because we have to take the complex conjugate in the Fourier decomposition, and there's going to be a minus sign here. So what do you get? You get 1/2 times the integral d3x, integral d3y of e to the I k, e to the I kx minus k prime y. And here you get a delta of x minus y minus delta of y minus x. And minus delta of y minus x, well, that's just another name for delta of x minus y. So you get two factors of delta of x minus y, which cancels that factor of 1/2 out front. You can use that delta function to do one of the integrals, and you get an integral d3x. Say we use it to do the y integral, times the integral e to the I x mu of k mu minus k mu prime. And what is that? That's just the Fourier expansion of the delta function that sets k equals to k prime. So what have we done here? We've rediscovered the commutation relations of the simple harmonic oscillator. Okay. These are precisely the commutations that we derived last week when we constructed the Hilbert space, that is to say the Fock space, of a multi-particle system directly just by demanding that we have multi-particle states that behave in the sort of nice way that we would expect. Okay. So just to conclude, we have an infinite number of simple harmonic oscillators, one for each momentum k. And we saw that the simple harmonic oscillator algebra, which was something that I just sort of pulled out of a hat last week, is actually something that follows in a completely straightforward way from the quantization of a free real scalar field theory once you impose the canonical commutation relations of quantum mechanics. Question?
What happens to the e to the I omega t?
Oh, yeah, I'm evaluating everything at time t is equal to 0. Right? Because remember, these commutation relations are really understood as t equals 0, time t equals 0 commutation relations. Good. Yeah, I don't know if we'll get to it. We might get to it this class. We'll start discussing commutation relations when not, for operators that are not at equal time. Good. Good question. Other questions? Computations like this are sort of the bread and butter of quantum field theory, so you should get used to them. Actually, they're not even the bread and butter. They're the crackers and cheese that come before the bread and butter. Okay. Any other questions? Good. Okay. So what does this mean? This means that the Hilbert space of a free quantum field theory is indeed the Fock space that we constructed last week, where you start with the vacuum state, which is the state with no particles in it. Then you add to that the one particle states, where you take just a single raising operator acting on the vacuum, the two particle states, where you take two raising operators acting on the vacuum, and so on and so forth. The general state in the Hilbert space will be some linear combination of states like this. Question?
If you have this commutation relation, if you move an for example, A and its dipole.
Yes.
If this commutation relation is the delta function,
Yes.
then we can assume that they are the creation combination.
Absolutely, absolutely, absolutely. So, yes. So, okay. So, yeah. So maybe it's probably worth, okay. So this is really, in quantum, so in quantum mechanics, if you just have a single raising and lowering operator that obey this algebra, and you try and construct a Hilbert space from this algebra, and if you in addition demand that there is a ground state, so a finite energy ground state, you have to assume some form of the Hamiltonian to make that statement. But if you assume that you have this algebra and you have, say, a Hamiltonian proportional to A dagger A, and you demand a finite energy ground state, then there's only one possible Hilbert space. It's the Hilbert space where you have the vacuum state and the various n particle states, or I shouldn't say that, n excitation states that you get by acting on the vacuum state with these raising operators. Okay. If you don't remember that derivation in quantum mechanics, go and, as soon as this class is over, don't go to dinner, just go and like read Griffiths or Sakurai or whatever book and remind yourself of that proof, because that's very important. Okay. Does everyone remember that proof? No, you guys do not remember that proof. Okay. You should, yeah, okay, good. Well, it's good I haven't written the next problem set yet, because you will be going through it again on your next problem set. Good. Okay. You guys really don't, okay, that's like the most important thing that you ever learn in quantum mechanics. Okay. It's like more important than the Born rule. Okay. That's not true. But it's like the second most important thing that you learn in quantum mechanics. Okay. Should we go through the proof? Can I remember? Should we go through the proof? Should we do it? Can I do it in real time? I probably, yeah, okay. We can do it. Do you want to do that, or should we continue?
Put on the homework.
I'll put it on the homework, yeah. You guys have done it in quantum mechanics. I guarantee. How many of you at least recognize this from your quantum mechanics class? Okay, yeah. So you're going to review it again in real detail on your problem set. Don't worry. Okay. Excellent. Any other questions? The more questions you ask, the more ideas I get for your next problem set. So keep asking. It's always hard to come up with good problems. Okay, good. So what we've seen is that the Hilbert space of the theory is just that of a bunch of harmonic oscillators. What about the Hamiltonian? Okay. So in particular, I computed for you the Hamiltonian of free classical field theory. It was just given by where was it? It's just given by this expression here. Okay. So let's see what this looks like in terms of the raising and lowering operators. Okay. And hopefully you're not going to be terribly shocked when I tell you that it's exactly the same Hamiltonian that I wrote down for you a week ago when we sort of just directly constructed the Hilbert space and the Hamiltonian of a non-interacting free field theory. So in particular, let's just go ahead and consider this quantity, AK dagger AK. So what was AK? So you just go ahead and use this expression here. So it's the integral d3x of e to the I kx, and then you have the phi plus pi. So AK times AK dagger, you get an integral d3x, an integral d3y, times an e to the I, well, a k mu x, let's see. Here, here, let's do it, let's write it this way. You get a minus k mu x mu from the AK dagger, and then a plus k mu x mu, k mu y mu from the AK. And then you have, well, let's just go ahead and remind ourselves of that formula again. You had phi of x plus I pi of x. And so you get here a square root of omega over 2, phi of x plus I over the square root of 2 omega. Did I get that right? Did I copy the formula right? Pi of x Did I copy that formula right? Let's take a look here. Oops, where was it? There it is. Yeah, plus I over 2 omega pi. So we get a minus sign here because we were taking the Hermitian conjugate, and we get the same terms with x replaced by y here, and with a plus sign because there was no Hermitian conjugate. Sorry, that's a y. Okay. So if you look at this AK dagger AK, there's a couple of terms that look pretty good. Okay. So in particular, there's a pi of x times a pi of y term here. That looks pretty good. But you also get terms that are cross terms that look like I pi phi. So what we want to do, and the reason why we have those cross terms is that what we've written down here is actually not a Hermitian operator. To get a Hermitian operator, what you need to do is take things like ak dagger, ak, plus its Hermitian conjugate, ak dagger. So that'll automatically get rid of all those terms with the factors of I out front. And then what I want to do is multiply this by omega and integrate it d3k. So what do you get? Well, the first thing that you get is you get those pi terms. What do those pi terms look like? You get a pi times pi, and you get an integral d3. Well, let's just look at the pi terms first of all. So this omega here will cancel the two factors of 1 over square root of omega in front of those pi's. So you'll just get an overall factor of pi of x times pi of y. And then you can use the d3k integral. So that d3k integral turns into a delta function that sets x equals to y that we can use to do the y integral. And you get an integral d3x times 1/2 pi of x squared. Okay, that's already looking pretty good. That's the first term in the Hamiltonian density, which was 1/2 pi squared. Now you get the phi squared terms. Those are a little bit more complicated because you have an integral d3x, integral d3y. You get a 1/2 out front because the two factors of 1 over root 2. And you get omega squared times phi of x, phi of y, times that phase factor e to the I minus I k mu x mu minus y mu. Oh yeah, and we also have an integral d3k, sorry, d3k. Here. I'll just write it up here. Okay. Now if that omega squared weren't there, we could just use the k integral to turn that into a delta function that sets x equals to y. And then we would have just an integral d3x. But the problem is that we have an omega squared there that depends on k. So what is omega squared? Well, it's k squared plus m squared. So that m squared term, we can just do the same thing that we did here, and what will you get? You'll get an integral d3x times 1/2 m squared phi squared. Okay, that's great. That's another term in the Hamiltonian. The only term that's slightly tricky is the term that involves this k squared here. And to do that, you just need to use a little trick. So remember what we're doing here is an integral that looks like the integral d3k of e to the I k of x minus y times k squared times phi of x, phi of y. And now you could use the trick that k squared times e to the I k dot x is exactly the same. So k times e to the I k dot x is exactly the same as the derivative of e to the I kx with respect to x. Okay. And then you could, we're integrating this d3x. And so you could do that x integral by parts to move that derivative acting onto the phi. And then to get the other factor of k, you could do the y integral. You could write that as the derivative with respect to y of e to the I ky, and then do that y integral by parts. And what you'll get then is, well, you'll get the integral d3x of the gradient of phi squared. Because now we've removed that factor of k squared at the expense of taking a derivative on these two phi's. And then you can use the k integral to set this into be a delta function that sets x equals to y. Use that to do the y integral, and you get this expression. So that this guy here is just going to be the integral d3x of 1/2 times pi squared plus grad phi squared plus m squared phi squared. Okay. Which is the Hamiltonian of a free field theory. So just to summarize, what we see is that the Hamiltonian of our free field theory is just given by the sum of the Hamiltonian of an infinite number of non-interacting harmonic oscillators. So the Hilbert space of the theory is a Fock space, which is that of an infinite number of simple harmonic oscillators, one for each momentum mode. And the Hamiltonian is just the sum of an infinite number of Hamiltonians of an infinite number of simple harmonic oscillators, one for each momentum mode. So this is exactly the conclusion that we arrived at last week when we did a sort of more direct approach to the quantization of a multi-particle system. The advantage of this approach is that we now understand, in at least in principle a straightforward way, how to generalize this to more complicated theories. In particular, we could now ask how we could include interactions. So, for example, what would happen if our Lagrangian were not just d mu phi plus 1/2 m squared phi squared, sorry, minus 1/2 m squared phi squared, but what if we included additional terms? So let's say we had a term that looked like phi to the fourth. This is going to be one of our favorite examples over the next few weeks. It's one of the simplest interacting theories that we could write down. What, schematically, at the very least, what would happen? Well, what would happen is that the Hamiltonian would look like the integral d3k of omega times ak dagger ak plus ak dagger. But then there would be more terms. There would be terms that are quartic in the A's. So, for example, there are terms that you would get if you went through that. So there would be terms. So if you just expanded phi in terms of the A's and A daggers, phi is linear in the A's and A daggers. So phi to the fourth will lead to terms in the Hamiltonian that would look something like ak squared, ak dagger squared. So if you think of the AKs as operators that create, and as AK as an operator that destroys a particle and AK dagger as an operator that creates a particle, then what do terms like this in the Hamiltonian look like? They look like terms that allow you to destroy two particles and create two other particles. Okay. So that would mean that you have interactions of the sort where two particles can come in and two particles go out. So this is why free quantum field theory is one where the Lagrangian is quadratic. It's because when you, for a quadratic Lagrangian, you expand the field operator in terms of solutions to the equations of motion. The field operator will be linear in the raising and lowering operators, the creation and destruction operators that create and destroy particles. But if your theory, if you're Hamiltonian or you're Lagrangian, has higher order terms that are not quadratic. These will lead to interactions that allow particles to interact with one another and to create, and so you can have sort of interactions where particles can bounce off of each other. Two particles can combine to form a third, a fourth, and so forth. So our typical strategy for studying these theories is that we're going to be imagining situations where this interaction term lambda is relatively small, and then we'll work out a systematic perturbation theory known as, well, we'll be deriving it in terms of Feynman diagrams for studying interactions in this quantum system. So that's sort of the general roadmap for where we're going over the next several lectures. Maybe I should pause here and see if there are any questions. Yes?
About expanding phi in terms of the solution state going into motion. And, those are solutions.
Yes.
Single particle.
Yeah, that's right. So,
So I mean that.
yeah,
so
you mean in an interacting theory?
No, I'm just wondering. I mean this
Yeah.
is a simple question, but when you write out phi like that,
Yes.
that doesn't impose any extra restrictions on phi, right?
That's right. I mean, if you want, you could think about the expression. I mean, so this is sort of the. Okay, you can. This is the. You can tell by all of the arrows. Okay, that this is the most important expression of the day. Okay. And the question is, so, and if you want to, you don't need to think about this as an expansion in terms of solutions to the equations of motion. It's just the Fourier expansion of phi. But why is the Fourier expansion an intelligent thing to do? Well, it's because the Hamiltonian looks very simple in Fourier space. Okay. The Hamiltonian is just k squared plus m squared in Fourier space, whereas it involves derivatives in position space. I mean, there's one important point that I should bring up, which is that, strictly speaking, when you include interactions, it's really no longer fair to talk about the Hilbert space as just being the simple Fock space of one particle state, two particle states, and so forth, created by the raising and lowering operators of this sort. In principle, the Hilbert space is going to become much more complicated. You could have bound states, you could have all sorts of complicated things going on. So we will have to be a little bit careful when we try and generalize this all to include interactions. But at least in your head, if you want a simple picture, you should really just think about these interacting theories as theories where you have a bunch of harmonic oscillators, but now the Hamiltonian has been perturbed slightly to allow these different oscillating modes to interact with one another. And it's literally the case that you will get terms that look like this, which will allow, in this case, two particles to come in and combine to create two other particles. Any more questions before I continue? So what I was planning on doing now is just going ahead and diving into the theory of interacting quantum field theory. But before I do so, there's one question that I wanted to return to, okay, which is the question of causality in quantum field theory. Okay. So remember, the very first week of this course, we saw that if you try and construct a single particle theory of quantum mechanics consistent with special relativity, what you'll find is that the theory inevitably allows you to go back in time and kill your grandfather, okay, which is not something that we like of our theories of physics. So before we continue, what I'd like to do is just confirm that this theory of quantum field theory based on a field variable phi preserves causality. Okay. And I won't have time to complete the argument. So what I'm going to do is show you an argument that looks awfully dangerous and shows you that particles can still travel faster than the speed of light in free quantum field theory. And then your homework assignment tonight is to go home and think about what the loophole is in that argument and why actually you can't go back in time and kill your grandfather. So let's consider the following quantity. Okay, I'll call it D. what it's going to be is the expectation value of phi of x, phi of y in the vacuum state. So remember, phi is the operator that creates or destroys a particle at position x. And so this is just the quantum mechanical amplitude for a particle to propagate from x to y. And I've called this quantity d. I've written it as a function of x minus y because, as we're going to see in just a minute, because of translation invariance, it can only be a function of the distance x minus y. And here x and y are points in space-time, so they're really 4 vectors that I should call x mu and y mu. So what is this quantity? Well, I just go ahead and plug into that formula that I wrote above and circled in a box and wrote a billion arrows pointing to. Okay. So what was that formula? That said that, here, I'll just rewrite that. So let's use the fact that phi of x is equal to the integral d3k over the square root of 2 omega k times e to the I k mu x mu. Just for the sake of convenience, I'll leave off that mu label just to make my formulas a little bit shorter, times ak plus e to the minus I k mu x mu times ak dagger. So let's just go ahead and plug that into this formula. So that means that d is going to be the integral d3k over the square root of 2 omega k times the integral d3k prime over the square root of 2 omega k prime times the expectation value in the vacuum of this at point x times the same thing at point y. And remember that AK annihilates the vacuum when acting on the ket vacuum state, and likewise when acting from the right on the bra vacuum state, AK dagger annihilates the vacuum. So the only non-zero term in this sum will be one with an AK on the left and an AK dagger on the right. And so it'll be multiplied by e to the I kx minus I k prime y. And then, of course, we can commute these guys through one another unless k is equal to k prime. If you can commute those guys through, then that's just equal to 0 because you can act on the vacuum state with the AK. So that means that k needs to be equal to k prime, and we get the commutator delta of k minus k prime, which we can use to do the k prime integral. So this d of x minus y is the integral d3k over 2 omega k times e to the I k mu times x mu minus y mu. And this is what's known as the propagator in free quantum field theory. It's the quantum mechanical amplitude for a particle to move from a point x to a point y. So next time we'll begin by manipulating this propagator and showing that in fact it's non-zero for points that are space-like separated. So if you want an exercise that you can do for yourself, go ahead and try and compute this thing for points that are space-like separated. It's a very simple generalization of the argument that I went through. It's in fact, almost but not exactly the same integral that I computed for you on the second day of class to show that you can go back in time and kill grandma, or maybe it was grandpa, using a single particle relativistic Hamiltonian. Okay. show that this propagator is still non-zero in the present case. And then if you're very clever, figure out why that does not contradict with causality. So let me maybe stop here just by seeing if there are any questions before we end. Yes. And also the other thing that you should do when you go home tonight is you should go to a tattoo parlor and get this tattooed on your forehead. Because it's a very important expression. Okay. See you all on Thursday.